1. Vectors. Hi everyone, and welcome to Shortcut to Physics Online. Today, we'll be diving into the topic of vectors. You've probably come across vectors before in math. But in physics, we'll see not only how they're used, but also why they're so important. Some of this might feel familiar, but it's always helpful to hear things explained in a slightly different way, and to reorganize what you already know. In this lesson, we'll explore 3 different ways to represent vectors. After that, we'll learn how to add, subtract, and multiply them, both graphically and arithmetically. Finally, we'll tie everything together by connecting vectors to coordinate systems in physics. And that's where we'll wrap up today's lesson. 2. Scalars versus vectors. Let's start by talking about the difference between scalars and vectors. We won't go into the heavy math here. Just the basic physics idea. A scalar has only magnitude, while a vector has both magnitude and direction. Here's a simple comparison. Scalars include quantities like mass, distance, and speed, just a size, with no direction attached. On the other hand, weight, displacement, and velocity require direction as well. So they're vectors. In everyday life, people often use speed and velocity as if they mean the same thing. But in physics, we'll keep them separate. Don't worry if the distinction isn't crystal clear yet. We'll cover it carefully as we go along. Other examples of scalars include time and temperature, while acceleration and force are key examples of vectors. Even your physics grade is a scalar. But if it keeps improving from 80 to 90 to 100, you could think of it as a vector pointing in the positive direction. Just a fun thought. 3. Why do we need vectors in physics? So, why do vectors matter in physics? If physics were only about objects that stayed still, scalars would be enough. For example, I can say, the book on the desk has a mass of 1 kilogram. But the moment things start moving, we need direction to describe them properly. If I say a car is moving at 10 meters per second, that tells us its speed, but not whether it's forward or backward. If instead I say 10 meters per second to the right, now we have a vector. It gives us both speed and direction. The study of motion is called kinematics, and it's one of the main areas of physics. Vectors are the perfect tool for describing motion. 4. Representations of a vector. There are 3 main ways to represent a vector. First, when writing vectors in text, we usually put an arrow above a letter, like a. Remember, a vector always has both magnitude and direction. The first method is graphical. Simply draw an arrow. The length of the arrow shows the magnitude, and the arrowhead shows the direction. It's the most intuitive way to think about vectors, and it's very useful for solving problems visually. Now, here's something really important to keep in mind. A vector doesn't depend on its position. Think about it. Very thing that defines a vector is just its magnitude and its direction. So, wherever you draw the arrow, if the magnitude and the direction are the same, it's the same vector. And this idea will actually play a really big role later on, when we start working with vectors graphically. The second method is polar representation. This means we give the vector's magnitude and the angle it makes with the positive x-axis. For example, a vector of 10 meters per second pointing northeast can be written in polar form. 5. Position vector. The third way is through a position vector. Here, we place the vector's tail at the origin, 0, 0, and use the endpoint's coordinates, x, y. So we draw it from the origin to its endpoint. This approach lets us treat vectors like numbers, which makes calculations much easier. The x and y components connect directly to the vector's magnitude and direction. In fact, the magnitude comes from the Pythagorean theorem, and the angle comes from the arctangent of y over x in trigonometry. So, the same vector, say 10 meters per second northeast, can be shown as an arrow, in polar form, or as a position vector with coordinates. 6. Vector addition. Vector operations can be done graphically or arithmetically. You've probably seen this in math before. So let's just review quickly. First, vector addition. Graphically, we use the tip-to-tail method. Place one vector's tail at the tip of another. Then draw the arrow from the starting point to the final tip. This works because a vector's value doesn't depend on where it starts, only on its magnitude and direction. Vector addition is also commutative. Vector A plus vector B equals vector B plus vector A. Another graphical method is the parallelogram method. This idea will become especially useful later, when we decompose vectors. 7. Scalar multiplication. Next, vector multiplication. In mathematics, there are two kinds of vector products: the dot product and the cross product. But here, we'll only cover scalar multiplication. This simply means multiplying a vector by a number, which changes its size but not its direction. You can double or have a vector's length this way. If the number is negative, the vector flips direction. For example, minus vector b is the same size as vector b, but it points in the opposite direction. 8. Vector subtraction. Now let's talk about subtraction. Vector subtraction is just addition with the negative vector. So, if vector d equals vector a vector b, that's the same as vector a plus minus vector b. Graphically, we flip vector b, then add it to vector a. You can also think of it as drawing the arrow that goes from vector b to vector a. This gives us a simple, visual way to handle subtraction. 9. Arithmetic method. Instead of using diagrams, we can also calculate vector operations arithmetically. The key idea is to use the position vector representation. If a vector is written as coordinates x, y, addition means adding the x components and y components separately. Scalar multiplication means multiplying each component by the number. Subtraction is just adding the negative vector. This arithmetic method will be very useful for solving many physics problems quantitatively. 10. Vector decomposition. Now let's look at an important application: vector decomposition. This is basically the reverse of addition. Any vector can be broken down into two components, one along the x-axis and one along the y-axis. This is the foundation of using position vectors in a coordinate plane. For example, vector A can be split into vector x and vector a y to I. In other words, vector A equals vector x plus vector I. Since a vector's value doesn't depend on where it starts, we can place vector A at the origin and express it as x and y coordinates. This method of using coordinates and components will be the basis for solving many physics problems. 11. Coordinate system summary. Let's wrap up with a quick summary. As I said earlier, any vector A in a 2D plane can be split into vector x and vector I. If the magnitudes of x and I are small a and small b, then vector A can be written as a, b in position vector form. If the magnitude of vector A is capital A, and it makes an angle theta with the positive x-axis, then in polar form it's a, theta. These forms, small a, small b, and capital A, theta, are related through trigonometry. From right triangles, we know how sides and angles connect. This relationship will come up again and again in physics, especially when solving problems. That's everything we need to know about vectors for physics. Good luck!